Hello, if I'll just chat to this video. I'm very happy you can join me for this one. In this video, we're going to bring in an NACA0012 airfoil for the reason that we can now safely run it up against the NACA009 airfoil and compare parameters of interest that is. So in the last video we finished off the grid convergence index study and we determined that the grid as laid out in design point 3, or this level of refinement, has returned one in which we are most confident that the discretization error within our discretized flow domain is at a level there that we can live with. So our GCI value was adequately low and our apparent order was still at a value that we could be relatively confident with, that numerical inflation or any sort of artificial inflation hadn't taken too much of a major effect in it. So now that I have a discretized domain, I have a canvas now that I can lay a number of different airfoils down upon and run a computational fluid dynamic analysis and compare parameters across the different airfoils. Now, this is kind of getting back into what the original motivation for this playlist and this series was, which indeed was to determine what might be the optimum or the most optimum with respect to what we're going to look at, airfoil profile or profiles for use on a STEM racing car, or a car that will be developed for the STEM racing competition in the front wing. We have compared the NACA 0009 and now it's time to compare other airfoils against it and see how it stacks up. We have to be sure that we're also going to use the same input parameters, so we are comparing like for like. Our angle of attack obviously is going to stay at 0 degrees. Our velocity we're going to keep the same from airfoil to airfoil, and as I said, we'll ensure that we're laying it down on the same discretized domain. So in our last video, this is where we finished off with 4 design points. We initially had a coarse, a medium, and a fine mesh, and out of the fine mesh, we did get a fairly good GCI value, and our apparent order was decent enough. But we did refine it one more, and when we did refine it one more, we were still at a level where numerical inflation didn't take hold and our apparent order value did not explode to something that was nonsensical. Whilst our GCSI index came down to a very attractive level, and we decided there that DP3 is the design point that we're going to run with. So despite having more mesh elements in our discretized domain, I'm fairly confident that the PC that I'm running this evaluation on can handle it, given its processing power and the RAM, which is not extravagant, but 165,600 elements is not an extravagant number either for these type of evaluations. So what I'm going to do is I'm going to select DP3. I'm going to set that as my current design point, which means there that anytime I go back into the Fluent solver, or I check into my solutions file, or if I did bring in a post-processing and results, it would be the results of DP3 that I'm looking at. So the way you do that is just click on to the design point or the row of the design point that you want to set as current, right click it, and you set it as current. Now, I cannot set this as current, and I know why. It is likely because, and of course I didn't select retain to retain the values of that design point. How did that happen? Well, when I initially set out my coarse, medium, and fine mesh, yes, I did click to hold this data on. But when we decided that we would refine it one step further and we created this new design point, I didn't click retain for this one. So having clicked retain on that, I'm going to right click this, and now I'm going to set this as current, which it is. Now the odd time you do that, if you don't retain data and you retrospectively retain data after a calculation and then you go to set that design point on as current, you may get an error, not an error that comes up, but a splash screen that'll come up to advise that it isn't able to set that as a current design point unless the profile or the specification for updating parameters is swapped over to update full project. So the way you access that, if I just click out of that brave and quick, is you come back onto your project schematic, right click onto your parameter set, make sure the properties are hit, and down here you'll see retain design point value. You might have to change that to update full project. When you do that and you come back into the parameter set, you will not have a problem then switching that to current. However, we will have to recalculate. So that's what I'm going to go on ahead now and do before anything else. Is I'm going to right click this now, and I'm going to update selected design points. Clicking that has started our calculation, and it should take maybe about 3 or 4 minutes, I'd reckon. But as opposed to having you hang on with me while this happens, I'm going to go on to pause, and when it's completed, I'll come back and we'll take it from there. Okay, back again. So as suspected, it didn't take an awful long time. It's just finishing off the calculation there now, but scrolling over here to the right hand side has revealed that my values have adequately updated for the parameters that I've set to output. And there it is now, set in as current. So what I'm going to go on ahead to do, actually what I will do is I'm going to go to File, I'm going to Save As, because I don't really want to undo my so I'll go back onto the documents here. I don't really want to undo my files here for my mesh independent study up to that. So I'm going to do is this one. I'm going to take off the 25 chord, and I'm going to go for NACA 0009 and then call alternatives. And I'm going to do it like this here. _V alternatives. And we're going to call this, bring in alternate airfoil profiles, and we'll compare it against the NACA 0009. What I should have done, and what I will do retrospectively on my own time after this video, is I'll reopen this file and I will archive it. So I went through archiving there in an earlier video. So you go into File, and then what we'll do is we'll archive it here. And then I'm going to move it onto my OneDrive just to keep it safe, and then I'll be able to take it out of the C drive off the computer. So again, even though OneDrive syncs into the C drive, you should do your ANSYS Fluent evaluations on a non-syncing C drive, even if you select to keep the files on the computer all the time as part of your OneDrive management. Do it and save them in a dedicated folder in the documents or somewhere on the C drive on your computer, and when you're done with it, then archive them, bundle them up, and then save them up onto your OneDrive and access them then as you need them out of the archive. But don't rely on writing files on a shared drive, like a cloud to local drive share. Well, anyway, now this is NACA 0009 versus alternatives. What I'm going to go ahead and do is I'm going to delete out each of these design points here. So I'm going to click onto that, and I'm going to delete, and click onto that, and delete, and click onto this one, and delete. All right. So now I have just design point 3, and I have a whole list of parameters here, some relevant and some irrelevant. What I mean by that is that we left in things like lift coefficient, and we left in pressure coefficient and all, just that we would have multiple parameters to compare from design point to design point. But now when we're dealing with one design point, we don't need all them parameters to compare. Now, yes, we are looking at a couple of different airfoils, and you say, well, why don't we compare them parameters from airfoil to airfoil? And normally you would. However, in our application for STEM racing, lift coefficient and indeed lift force is not really something that I should concern myself with, because if anything, it should be negligible. It shouldn't be there at all, but like, we're never going to get a zero lift force, let's face it, on this. It will be there, but it should be, for all intents and purposes, zero. It is not lift that we're really looking to achieve in our STEM racing setup for our car, albeit a wee bit of lift, as I've always said, does not hurt once it is lift and not downforce. And same thing with pressure coefficient. The thing there that I am really concerned with, that I'm really interested in, is the drag coefficient and the drag force, because when I pull the trigger and I shoot the car down the 20-meter track, after about 0.4 of a second, I'm out of gas. Right? The 8 grams of CO2 is now exhausted, and I've lost thrust. So I'm going to be at my maximum speed at that point. When I lose force and I lose thrust, obviously I've lost acceleration, and I am going to start decelerating, obviously because of losses, because of two main elements. One is going to be rolling resistance and the friction that comes with that, and the other there is obviously air resistance, which is also another form of friction. The rolling resistance I'm going to try to minimize by looking after my wheels very well, and the axles and the bushes and so on, and just make sure that the wheels go round as handily as possible, as kind of uninfluential as possible. And what I also want to do, obviously, is minimize my drag. Right, so this is what I'm going to look at. I'm going to look at the drag force here. I know the drag force here for an NACA 0009 airfoil running at that velocity, at my peak velocity, even though that is slightly below. I reckon roughly about 40 meters per second is probably our peak. I have them values right here. Drag force, there it is there. I want to compare that against another airfoil, and whichever has a lower drag. And providing that airfoil and the setup of that airfoil, its geometry is within regulations, that's probably the one I'm going to go for. The one there that has the lower drag force is the better airfoil for our application. So that's exactly what we're going to do. So what I want to do now is I want to get rid of some of these other parameters that are not needed. So what I'm going to go on ahead and do is I'm going to go into solution. I'm going to double click that, and I'm going to take myself in. This will launch the Fluent Solver. And I'm going to turn off or get rid of, delete out, well, I'm not going to delete the definitions for, but I'm going to delete the reporting out to the design table of all irrelevant output parameters and all input parameters. So I'm going to, that I don't need, leaving only the ones that I want to compare. So this will kick off now. There we are. So we can see down here in the bottom left in my tree, parameters and customizations, we can see parameters and indeed input and output parameters. Now you'll find I can't delete the input parameters. So if I click, for instance, angle of attack, I right click it, it gives me view, doesn't give me an option to delete. However, an output I can. Characteristic cell size, yeah, I can delete that. Don't want to report that out anymore. Drag coefficient, yes, I want to keep. Drag force, yes, I want to keep. L over D, no, that should be hopefully 0 or as close as possible to it, because L should be as close as possible to 0 for a 0 angle of attack airfoil. L over D, let us hit delete on that, yep. The force again, L over D, delete. Coefficient, delete. I'm going to keep my max Y plus because I also want to make sure that when I bring in new airfoils onto this discretized domain and I re-establish the meshing based on the edge sizing that's been set up, that for a different profile of airfoil I could potentially have different mesh dimensions or different cell dimensions. I just want to make sure that you know, that they're all low enough to make sure that the turbulence model, which I'm using the SST again on this, that the turbulence model is still remain robust for it. So again, I want to make sure that my Y plus value does not exceed 1 anywhere along that airfoil if possible. So that's what I'm going to keep that one for. Pressure coefficient, delete, don't want that one. And my Reynolds number, don't need that. Okay, now the inputs here, as I said, I can't take them away. I can leave them on if I want, but just don't want to bother looking at them. Those were created in named expressions, so there they are: A of A, cell count, velocity inlet, cost A of A, and sine of A. Now obviously I won't be able to delete this here either, so if I go into named expressions, click on named expressions itself and hit manage, and I go to A of A and I hit delete, I won't be able to. Why? Because A of A is used for in different functions here, in different expressions. The cosine AA and sine of AA, which is required by my setup in order to calculate the lift coefficients as well as the drag coefficients, which even though I'm not reporting the lift coefficient out, I'm still calculating it, okay, and I'm calculating that in the report definition. So I still need to keep that. I cannot switch off A of A there. But what I can do is I can come into edit the A of A and I can untick it here as used as an input parameter. Okay, now it's not. Same thing there with my velocity inlet, right? I'm not going to want to use the velocity inlet. I know what it's going to be. I'm not going to change it. I'm going to keep it the same as it is. And if I do change it, I'll go into the solver itself and I'll change it once. All right. Now this here has gone blank. This here will catch out, I'd say maybe 3 out of 5 is. You're going to click that next and things go blank. The only reason it's gone blank is because you have two things ticked. So untick off angle of attack, you have velocity inlet. Let's hit edit. use as input parameter and take that off. Okay, that's still now gone. Right, let's close that off. Now I can X out of that once I have these. Oh, I'll tell you what we'll do. We'll just make sure that our values are what they should be. And I'll come back into angle of attack and it's set at 0 because I'm not going to be able to read these in the table now. Let's just make sure they are what we want. Angle of attack is 0, which is good. And then my velocity inlet here, we're going to specify 29 meters per second, which is fine. Okay, let's X that out. Close down Fluent. And here, yes, we're going to save this for current and future calculations. So let's X this down, come back onto the project schematic. And what we're going to do then is we're going to take a copy of our NACA 0009 geometry and mesh, and we're going to reallocate it. We're going to use it as the basis for an alternate geometry, which will be our NACA 0012. Right, but first thing before I do that, I can see there. You see this here is component system. This workflow. This is A and B, system A and system B. Come into the parameter set. This is set up here as A1, and B1. Right, so A1 here is going to be our mesh and our geometry, and B1 there is obviously our fluents. Now, what I'm going to do is I'm going to double click into, I won't do it just now, because it's going to be copied across. Yeah, I'll do that after. Come into project, I'm going to right click onto mesh, right, and I'm going to hit duplicate. Now when I hit duplicate, it's going to put in a new component system underneath this. And it's going to give it as a copy of this component system. Now I'm going to change that. It's not, I don't want a copy really of that. What I want to do is I want a NACA 0012 airfoil to be represented in this component system C. Now obviously I'm going to have to change my geometry because the geometry is still that of an NACA 0009. So I will go in and change that, and I'm probably going to end up doing this over in the next video. I'm just going to set it up here for the next video in which we can do the final comparisons. However, when I have brought that in, because C is a copy of A, when I look into the parameter set now, I can see here that my for A1 and C1 I've repeats here. Mesh divisions aft, mesh divisions wall, inlet and general flow field. Obviously we've set them up already, but the copy here has gone back and it's just recognized them as edge divisions. So what I'm going to do is I'm going to click into this one, into system A1, which is a 0009, and I'm going to postscript NACA NACA 009 into that. Control C. I was actually discussing NACA versus NACA with somebody less than 2 hours ago, and it's just stuck in my head. That individual was fairly adamant that NACA could be used. I didn't fully disagree with him, but I didn't fully agree either, needless to say. But what I will say is he hasn't convinced me to start calling an ACA NACA just yet. For some reason there I just lost that in the copy and paste. Control C, F2 to the end, Control V, and there it is there. All right, so these are all they're for the NACA ones now, and ACA ones. So what I'm going to do now is I'm going to match the 180 to the 180. So for that one, I'm going to Control C the whole lot of that one, and I'm going to Control V it into there. But I'm going to F2 that, and I'm going to call this NACA 0012. I suppose NACA rolls off the tongue a wee bit better, but till NASA or somebody else definitely says call it NACA instead of NACA, I'm going to stay with NACA. The NACA is what it was. You'd never hear the NASA, you just hear NASA. That's because there's no the before it, a definite article. So the 220 to 220 is the aft divisions. I'm going to Control C that one. F2 and V, F2, and then take off the 1, 2. So there's the mesh, there's going to be the aft divisions for the 120. Now these are both 120s. I don't know which is which, and I won't really know that until I go in and I make a change in the mesh system itself. So I'll set one of them to be 100, whether it's the inlet size here or whether it's the aft size there. This divisions on the aft, divisions on the aft. Ooh, where do we have these here? Seem to have doubled up. This I do not know why I have doubled that up. Right, it looks like I'm going to have to make multiple changes to that. I did not realize, I didn't see that coming up. What I will do, however, is I can open up another instance of Workbench and I can just check it up against the other ones. I'll check that up, I'll fix that up there in a wee bit when I turn the video off before we move into the next one. And that will be that one then completed. Okay, so I'll make that change after. But in the medium, what I'm going to do now is I'm going to take a copy of this one here as well. I'm going to duplicate that. Should upstream connections be kept for the process? No, not really worried about that. What was that asking me? It was asking me, should I pull the mesh out of system A into system D? I'm going to put that one there. And I'm going to do a likewise thing. I'm going to pull this mesh here into the setup of here. So I can even rename this one here now as well, Fluent for the NACA 0009. And this one, come on. This is Fluent for the NACA 0012. Right. Now, as I said in one of the first videos, or certainly the first video when we came into ANSYS Fluent, that I always use the component system as opposed to the analysis system. The way it's set up here doesn't really matter if you use component analysis because I'm running meshes straight into Fluent into two occasions here. But there is occasions where I might have a certain setup here. I might, for instance, use as I am a steady solver here, and here's a transient solver, and I might want to run that mesh into the steady solver, and I also might want to run it here into the transient solver and look, compare the two results. That's why splitting them up sometimes it gives me the added flexibility that we can run with that. So but we're not doing that there, so I'm going to delete it off. And very similarly, I can compare an NACA 0009 into this physics and an NACA 0012 into that physics by dragging and dropping there as well, taking that one off, for instance. Okay, so I can. That's why sometimes the modular nature of using the component systems can be advantageous, but it doesn't lend to what we're doing just now, so I'm not going to do it. And that's why using the analysis systems in this sort of an application would be every bit as robust. Okay, now the NACA 0012, I'm going to have to bring in a new geometry and a new mesh for that. So first thing we need to do is we need to determine what the geometry is going to be, what profile it is that I'm looking at. And what I would suggest to do on that to make sure we're comparing like for like is we'll go back to what we first looked at for the NACA 0009. And we found in the 009, according to the STEM racing regulations, which gives a minimum of a 2 millimeter thickness, using a 0009 airfoil, which is the thickness is 9% of the chord length, we would have had a run with a 22.22 millimeter airfoil chord length. Now, whenever we file down or we kind of sandpaper down our 3D printed airfoil shapes, what's going to happen is obviously we're going to be losing material, we're going to be losing thickness off this 2 mil, and we'll drop down below the regulated minimum amount. So what we did was we beefed that up. Now we needed to be careful for this airfoil because also our maximum chord length according to the regulations was 25 mil. We could run anywhere from 15 to 25. So if I bucked up the 2 millimeter and I bumped that up till 2.1, 2.2, 2.3, 2.4, 2.5, to allow myself a little bit of slack or a little bit of room to take material away. My chord length naturally is going to lengthen as well, and I could easily go over the 25 mil. So on the 0009 airfoil, we're at a limit, whatever we like. What we did find there is that a 25 mil chord, which is my max chord, I could run with 2.25. So if I did take material down off that, it would bring me down from the 25mm cord, which was my maximum cord. But still, you know, we're right up against the margins with that. There's not an awful lot of room for play on that. But what I will do is I'll go for a 2.25 thick airfoil for my next airfoil, which is going to be an NACA 0012. So given that the 2.25 will be 12% of the cord length, my cord length is naturally going to be shorter than the 25mm cord returned by the NACA 0009. So how is that worked out? Well, what I'll do is I'll come in here to my drawing tablet. I'll go into N and I'll say for a NACA 0012 airfoil. So at a 2.25mm thickness, and again why? Because that's the thickness that I use for the NACA 0009, and I want to make sure that I'm comparing apples for apples. A 2 thickness, the cord length will be given by this expression. So I'm going to go L cord is going to be equal to our 2.25mm divided up by 12%. So what does that equate to? Let's go into MATLAB here, and I'm just going to write it onto the command window. I have a 2.25 divided by 0.12, and I'm 18.75 mil. So as we suspected, a cord length is now shorter than what was returned for an equivalent thickness on an NACA 0009 airfoil. So that broadly gives me my parameters. I'm going to run with a slightly heavier. Well, it's a very badly drawn airfoil, but hopefully you can pardon me. I'm going to be running 18.75, and then at the thickness here, we're going to be running with 2.25mm. NACA 0012. Now the NACA 0012, there's been an awful lot of academic publications done on it around them Reynolds numbers, which is low speed. In and around the 40,000 to 60,000 of Reynolds number 50,000, where we're at right smack bang in the middle, for having particular tendencies to the formations of laminar separation bubbles. It does normally show reattachments on it, so it's not as detrimental as unattached ones, but it seems to be more prone to them than the NACA 0009. And of course other airfoils that might be sharing, you know, similar dimensional characteristics, you know, with respect to cord length and dimension. So running with the NACA 0012, again, I'm just using that because it's an easy one to generate using the 4-digit generator on Airfoil tools. We have plenty of data done on it, but there is other airfoils whose thickness is 12% of the cord length. So you're never going to be restricted to using the NACA 0012, but you know, it'll give us a good idea. You know, the other airfoils there, you know, it might be slightly heavier towards the leading edge, or maybe it might be slightly longer and tail off quicker, you know, towards the trailing edge. But they'll have different profiles. But again, the idea in these videos here is to give you a grounds now, and certainly in the next video, show you how to bring in alternative airfoils and run a comparative study. Which is what you want to do. Okay, so what I'm going to do there, we're just coming up onto half an hour now. I'm going to cut this video at this, just in setting this up and how we determine what our NACA 0012 dimensions are going to be. The next video, what we'll do is we'll go into Airfoil tools, we'll put that into the 4-digit generator, we'll get the points, and we will repeat really what we were doing in a much earlier video and bring in the new geometry in, and then we'll match the mesh of the new geometry mesh in system C to what we had in system A, and yeah, just simply go into this and we'll run it, and let's see how the two compare. So again, thanks very much for sticking with this one, and looking forward to the next steps in the next video. Thank you.